Hey guys, today we're going to talk about what inductance is. So inductance is when an EMF and a current are created due to a change in magnetic flux. So when we talk about inductors and if something is good at being an inductor, we're talking about how efficiently that material can induce an EMF or a current in another object or in that same object. Now that might seem a little confusing right now, so we're going to go over two different types of inductance that should help to explain that. The first one that we're going to go over is mutual inductance. Mutual inductance occurs between two different objects. So here I'm going to draw out two wires. First one we're going to label wire 1 and the second one wire 2. So let's just say wire 1, we start to send a current through it. Now, what we know from our lessons on magnetic flux is if you change a current going through a wire, you're going to change the magnetic flux. So in the instant that you turn on wire 1, in that time that it goes from having zero current going through it to the proper amount of current that it is going to end up with, you're going to be changing the magnetic flux. So I'm just going to draw here the magnetic field. And if wire 2 is close enough, it can actually feel that change in magnetic flux. Now what we've learned from Lenz's law is that objects are going to want to resist a change in magnetic flux. So what's going to happen is wire 2, to oppose that change in magnetic flux, is going to create a current going in the opposite direction of wire 1. Now, this current might not be as strong, or sometimes it can actually be stronger depending on the mutual inductance, sorry for misspeaking, mutual inductance between these two objects. Now, we can quantify it. So we'll say we know the EMF 1, which is of wire 1. So we want to find EMF 2. How big of a change in voltage is there going to be? So as an equation, EMF 2, so that change in voltage, that voltage that's going to be induced in wire 2, is going to be equal to negative M, which is the mutual inductance between two objects, over the change in current over the change in time. So what we learned from this is that if you change the current in wire 1 to be large, or if there's a large change in current, or if that change in current happens in a small amount of time, you're going to increase the EMF. The other factor that goes into this is the mutual inductance. This coefficient of mutual inductance is a constant depending on what the material is, so it changes depending on what material you're using. So we measure this in henries, or H as it's abbreviated. So as we can see here, if you have a large M, then you're going to have a large change in voltage in that second wire. There are depending on the device that you have, you might want to have a large M or a small m, but say that you have a coil in a device that is going to be having a change in current going through it, and you've got other wires. Let's just draw some other wires in here that go by that coil, but you don't want to induce a voltage in those wires. What you can do is, as you wire that first wire, you can then take the wire and send it going backwards the same way. And as the EMF going one way changes and induces an EMF, the magnetic flux created going when the current goes the first way is actually going to be canceled out by the change in magnetic flux once it starts to go backwards. So the overall change is going to be very minimal, and the wires around it are not going to feel a large change in magnetic flux. The second type of inductance that I'd like to talk about is self-inductance. Now, as the name says, self-inductance is an inductance that happens within one object. It does not happen between two different objects. So say we have a wire, we have a coil, and then continues. So, say that one increases a current going this way. Now, since we've got a wire here, and we increase a current going one way, we're going to have a change in magnetic flux. And what we learned from before, according to Lenz's law, when you have a change in magnetic flux, you're going to have resistance to that magnetic flux. Now, self-inductance is when you've got this coil here. And what will happen is as that current changes going through that coil, you are going to have a EMF that is created that is going to resist that change in current. So as this current starts to increase going through or starts to decrease, well, actually, let's just say it's increasing in this case, then this coil is actually going to create an EMF that goes against it. So basically what that will do is it will just take that device slightly longer to turn on. Now you might be asking, why is that helpful? Well, let's look here. Let's just say we have a light bulb. And that light bulb is just hooked up straight to a battery. And then over here, we have another light bulb. And this one too is hooked up to a battery. But in addition, it's a very ugly light bulb. I'm going to redraw that. But in addition to just having a battery, we're actually going to have an inductor. So let's look. Say we've got this light bulb and it's on, both of them are on. And then we detach the battery. With the light bulb on the left, the instant you detach the battery, boom, the light's going to turn off. However, with the light on the right, there may not be any more power coming from the battery, but due to that inductor, it is going to be resisting that change from current, whatever it was before, to zero. So it's going to keep a slight current going through that wire for a little bit longer. So the light on the left is going to turn off immediately, but the light on the right is going to keep glowing for a little bit more time, and then eventually will shut off as well. We can quantify how strong of an EMF is going to be created, just like in mutual inductance, with the equation EMF is equal to negative L times the change in inductance, change in current over change in time. So, like before, we have the change in current and the change in time, and then L is going to be the coefficient of self-inductance. That is also going to be measured in henries. And just as before, if you've got a large L, you're also going to create a large EMF. Now, there are several different things that you can do to change that L. You could have a small coil or a large coil. And actually, depending on what you put inside of that coil, will change the self-inductance as well. So if you were to put an iron core within a wire, that would actually increase the inductance of it quite a bit. Now, I've got a bit of a practice problem, so we can check and see how to use these equations. So let's say that you have a wire, and its inductor has a self-inductance of 35.35, 0.35. The current that is going through the wire, or that needs to go through the wire, is going to be 5. And the amount of time that it takes for the current to go from 0 to 5 is going to be 0.05 seconds. I'll give you guys a second. You can either pause the video or just work it out real quick and see what it should be. But the EMF that is going to be produced is going to be negative 35 volts, which is impressive that you can create a voltage of 35 volts from just an inductor. There are some ways that we can apply this to real life. These inductors can be very useful in our daily lives, and one of them that's near and dear to my heart is photography. So if you guys have ever been to a wedding or any big event where they've got the nice fancy cameras that I'm going to attempt to draw over here, you know that those flashes are super bright. Now, the way that this can work is teamwork between inductors and capacitors. What will happen is that this flash can actually be powered by a very small voltage battery, but the voltage of the flash can be extremely high. The way that this can work is that the current will be sent through an inductor, and that inductor will be made so that it will increase that EMF to be very high. Then a capacitor will store that higher voltage to be released at the moment that the person takes a picture. What's interesting is that if you take a lot of pictures very quickly, the flash will not shoot for a couple seconds after you've shot it once. So you need to take time between taking photos with these large flashes. And that's because the inductor needs the time to build up the voltage in the capacitor to be released. There is an equation for the self-inductance, so if we want to figure out what that L is going to be, it is defined as, N times the change in flux over change in current. So we can see here that if you have a larger coil with more coils to it, you're actually going to increase your L, which is then going to increase the EMF. There's also an equation that we can use to find the energy stored in an inductor. So say you've got this camera over here and you want to know exactly how much energy is going to be stored inside the inductor that then can be taken to the capacitor. And that is energy of inductance is equal to 1/2 L times current squared. So I'm going to give you guys another practice problem when it comes to this. So let's say that L is equal to 1.5 and the current is going to be equal to 25 amperes. I'll give you guys a second to figure that out. So the energy that should come out there is going to be 468.75 joules. Alright, well thank you for listening to my video, guys. I hope this helps you guys understand what inductance is and how it can apply to our lives. Thank you.